whose talk will be on some existence and uniqueness results for infinite dimensional Fokker Planck equations. Please.
First, I want to thank the organizer for the invitation. I am very glad to be again to the Newton Institute. So this is a review talk. I want to review some results about Fokker Planck, existence and uniqueness. I will concentrate especially in the uniqueness, and I will refer about some works done in collaboration with Bogachev, Rechner, Shaposhnikov, and Stannard. First of all, before giving the plan of the talk, let me recall the definition of Fokker Planck equation and which are the main differences that arise in the infinite dimensional case. So I consider a stochastic PDEs. For the moment, I will not be precise about, so A will be linear, B and sigma will be nonlinear, but I will not precise anymore the equation. I will do later. But assume for the moment that this problem is well posed. So there is a unique solution that I will denote by XTSX. Then one can construct the transitions evolution operator, just taking the expectation of any continuous bounded function h on the solutions xtxx. One constructs in a usual way the transitions evolution operator. Then it is easy to see, it is natural that the transpose operator will act on linear functionals on CBH and in particular on measures, on probability measures. So given an initial measure zeta in pH, by pH I mean the set of all probability measures in H, one can define a measure mu t just taking P0 t star, the transpose operator of zeta. So in other terms, this is equivalent to say that mu t is defined by formula 1. That is, phi di mu t is equal to P0 t phi di psi di zeta. This is the usual way to construct an evolution sequence of measures. Assume for a moment that one is able to differentiate P0 t phi. This will not be true for any phi, but assume that for we know some classes E, capital E, of test function for which one can do this differential. And LT will be a linear operator. And then if I take I differentiate equation 1 with respect to t, you take the left-hand side, derivative with respect to t phi di mu t, is equal to derivative with respect to t P0 t phi di psi di zeta. Then I use the fact that the derivative of P0 t is given by P0 t LT, and I end up with this result, that the derivative with respect to t phi di mu t is equal to the integral of LT phi mu t. So this is the Fokker Planck equation. This is the Fokker Planck equation. For instance, when the space is finite dimensional, say H equal to Rd, and the mu t are absolutely continuous with respect to the measure Lebesgue in Rd, this reduced to the well-known continuity equation for the densities of mu t. Now, when H is equal to Rd, there is and B a sigma are regular, it is clear what Lt is. Lt is just the Kolmogorov operator, 1/2 trace sigma sigma star d square of phi plus Ax plus B dx of phi. And also in finite dimension, it is natural the choice of test functions. In general, one can take the space C2b Rd or the space C20 Rd. But in infinite dimensions, both the choice of Lt and of E are not obvious, because in infinite dimensions, the operator Lt has these difficulties that, for instance, A is unbounded operator, B is not very well defined. And also it is not clear that there exists the trace of sigma sigma star d square of phi. So it is not obvious the choice of the test function. So this is the natural difficulties that arise in infinite dimension. One has to handle this problem. So now let me give the plan of the talk. In the first part, I will assume that the stochastic equation is well posed. In this case, it is possible to choose Lt and D in an abstract way, and so to get always existence and uniqueness of Fokker Planck when the problem is well posed. However, this result is not very satisfactory, because the space of test function is not explicit. One would have an explicit test of test function in which to put the problem. And also, the form of the operator Lt is not a differential operator, it is an abstracted operator that will be defined as I will show by Laplace transform. So it is interesting to know, but this is not very satisfactory. So in the second part of the talk, I will consider a concrete differential operator Lt and a concrete space of test function. Then I will examine the two situations, when the SPD is well posed and also when it is not well posed. When the equation is well posed, there is a natural candidate for the solution, the Fokker Planck, just by generalizing what I have written before. So I take mu t equal the transpose operator of an initial measured zeta. But here it is not clear that existence and uniqueness, because one has to check that it is not clear. Even if there is a concrete definition of differential operator, it is not clear for that the derivative of 0t phi is equal just to Lt phi. So this is the first situation. The second situation, when the problem is not a priori, at least well posed, one will do the following. One take an approximating operator, an approximating stochastic PDE, then use tightness in order to show existence. And this in general is not very, very difficult. But now the solution one will obtain, in this case, is a weak solution. So it is related to, for instance, to the problem of martingale. It is related to a solution in the sense of the martingale. And remark that when you consider the martingale problem in infinite dimensions, still there is this difference with respect to the final dimensional case, that both the operator and the test functions are not explicit. You have to take a decision when you consider even the martingale problem in infinite dimensions about the choice of test function. Then for the uniqueness, as I said, I will concentrate on the uniqueness. I will present a general results that can be applied in some situations. I will illustrate some situation in which this result applies. So before starting with this program, let me write the Fokker Planck equation in a more suitable way. So it is very easy to show that the Fokker Planck equation you have defined before can be written in this more general form. Instead to take a function phi depending only on the variables x, I can define the Fokker Planck equation for functions of two variables. In this way, the Kolmogorov operator will be an operator depending on t and l. So will be an operator ku equal dtu plus ltu. Okay? And the space of test function will be a space of function depending both on t and on x. Now this is the differential form of Fokker Planck. There is also an integral form. Just by integrating this equation with respect to t, notice one thing, that since we are studying this operator in the space 0t times h, it is needed a condition either in 0 or in t. So I will choose a condition in t, a final condition. So this is the Kolmogorov operator defined in a space of test function which vanishes in t. And so I was saying, taking one can find an integral form of Fokker Planck just by taking integration with respect to t, and we end up with this formula. And we will work with this definition of solution of Fokker Planck equation. K ut, because k ut x mu t dx equal to minus integral in 0. There is not the integral in capital T because I have considered functions vanishing in capital T. Okay, so I will start with the first part of the talk, that is the case when the stochastic PDEs is well posed, and in the case I will show how to find in an abstract way existence and uniqueness of Fokker Planck. So there is a classical way when one is studying evolution equation depending in time, and when coefficients are depending in time, there is a classical way to define the semigroup starting from an evolution operator. This is the standard way. So assume that xtx is a solution of the stochastic PDEs. Consider the transition evolution operator, PST phi equal expectation of phi xtx, and then we construct in a standard way a semigroup S tau on the function depending on two variables ut. And so this semigroup will be defined in the space of continuous functions which are continuous in time and continuously bounded in space, and which vanishes at the final time. This is the usual definition to reduce a non-autonomous problem to an autonomous one. One constructs a semigroup as tau just as pt t plus tau u t plus tau x if t plus tau belongs to 0t, 0 otherwise. This is the classical definition, even in a classical study of evolution equations depending on time. When one wants to reduce the non-autonomous problem to an autonomous one introduces this semigroup. Now we define the generator of k of S tau, and you define the generator through its Laplace transform, as usual. So one can show that there is a unique operator k such that its resolvent is just the Laplace transform of the semigroup S tau. You see the integral is between 0 to capital T minus t instead of between 0 to plus infinity because due to the definition of S tau, if t plus tau is outside of 0t, this is 0. Okay, now one can show, this is not difficult, that k is an m-dissipative operator in Zt, and its resolvent set coincides with the wall R. The reason is that the integral is not from 0 to plus infinity, but from 0 to capital T minus t. Okay, now let me consider the Fokker Planck equation. So with respect to the abstract operator k and the abstract tensor function, which is the domain of k. The domain of k is just the image of this Laplace transform when u varies in all the spaces D. And so here you have this result that for any zeta for any initial probability measure theta, there is a unique solution of Fokker Planck. This was proved in the thesis of Manka in the case when coefficients are time independent, and in this paper with Rechner when in the general case when coefficients are time dependent. So I stress again that this result is useful for its generality, but it has the disadvantage that the space of test function and the operator are abstract. So let me go to a concrete formulation. So now I consider a specific stochastic differential equation. Here A is a self-adjoint operator for simplicity one, and also I will not consider the more general case. I could consider A depending on time, I could consider Q depending on time, but I think this equation is enough general to treat interesting equations as Berger's, Navier-Stokes, and so on. So let me consider this equation. Q is a self-adjoint, not necessarily of the trace class. Q is self-adjoint and non-negative. And in the first part, I will assume that the problem is well posed. In the second part, that it is not. So I define a concrete space of test function. I consider all functions, the linear span of all functions of this form, utx equal alpha t times phi of x, where alpha is just a function which is C1 and vanishes at 0. And phi is an exponential function, a general exponential function, but such that h belongs to the domain of A. There is another natural possible choice, is that of cylindrical functions, that is functions depending only on a finite number of variables with respect to a fixed basis. But let me consider this space EA 0th. So now I consider this Kolmogorov operator, k of u equal dtu plus the usual one alpha trace q d square of u plus ax plus btx dxu. And the domain of k, by definition, is just the space of exponential function, EA 0th. So let's see that k operates in this space. So take an exponential function, exh, then the derivative of phi is e h phi, and the second derivative of phi is minus h tensor h phi of x. So I can do a simple computation. I can compute the k of u, and I find the phi prime minus phi of t plus this term. So here you see xah is well defined because I have took h in the domain of A. But obviously this term is of linear growth. This is well defined, but of a linear growth. And then there is a term which is not obviously defined, which is btxh. So I have to assume that btx is integrable with respect to the measure mu I will consider. So we will look for probability kernel mu such that x is integrable because due to this term which is linear, and also btx should be integrable. So I will look for a solution of Fokker Planck equation in this class of probability kernels. So let me present a general result of uniqueness. Assume that sigma is a non-empty convex closed set of solution mu of Fokker Planck. I recall that this is Fokker Planck. Okay? Then sigma consists of a unique element provided the following run condition also. One needs that the image of k, recall that k is defined on the space of exponential function, is dense in L1 ht mu. I recall that ht is just 0t times h. And mu is defined because if you have a mu t dt, mu t dx dt, I will define mu as, in a natural way, as a measure in ht. On the rectangle and then in any space. So this result in finite dimension was proved in this paper with Bogachev, Rechner, Stannard, and then an infinite dimensional generalization in this paper with Bogachev and Rechner. So I will not give the proof of this theorem. I will only stress one fact which is very important for the proof. Let mu be any solution of Fokker Planck. Then k is dissipative on LPH mu for any p greater or equal to 1. This is very important because dissipativity will give an a priori estimate of the solution. So dissipative is really very important. And moreover, if it is dissipative, it's also closable. This is the general property of dissipative operator. So for any solution mu of Fokker Planck, the Kolmogorov operator is dissipative and closable in any LP. So the run condition means namely that k, the closure of k is M dissipative in L1 ht mu. Notice also another important properties that not only is M dissipative, but 0 belongs to the resolvent set of the closure. This is a typical feature of Kolmogorov of Fokker Planck equation. We distinguish the theory of Kolmogorov equation from the theory of invariant measure. When you are looking for invariant measure, often you consider the closure of some Kolmogorov operator with respect to some space LP with respect to the invariant measure, and you find in several situations that this operator is closable, and this closure is M-dissipative, but in general 0 is not in the resolvent set. This is a very important property. So this is important. I will just give the proof that in the case p equal 2, when then there is a standard way to go from p equal 2 to any p. Just to see that this properties is very natural, in fact. Take p equal 2. Then there is the usual properties of Kolmogorov operator that ku square is equal to u k of u plus q1 alpha dx u square. And now I use the Fokker Planck equation. So the integral of ku square is just minus integral over h u0 d zeta. And then, using both the properties, I find that 2 times integral of u ku is negative, because it is given by two terms which are both negatives. With respect to the case of invariant measure, there is the last term, the additional last term, so the situation is different. So now, how to prove the rank connection? I will recall some results, and then I will give the proof of a last result. So one possibility is to consider, a natural possibility is to consider an approximating equation. Approximating equation means that we will approximate the coefficients b, which can be very regular. For instance, in the case of Burgers and Navier-Stokes. So you take any regularizations of b, bn, for instance, Galerkin, and then consider the approximating equation 1. Since bn is regular, it is possible to show that this equation has a solution. For instance, one can give a probabilistic formula, just which is the formula 2. It is just where, so to express the solution of equation 1 in terms of the characteristics are just the solution of the stochastic evolution equation 3. Okay. Now there is a technical point which is a bit delicate, but it can be proved, that un, the solution of approximating equation, there is no reason that this solution belongs to the space of exponential function, but one can show that belongs to the closure of K. So it will not belong in general to the domain of K, but will belong to the closure of the domain, to the domain of the closure. And then one can write the previous equation in this form, because this equation was so one can show that this un belongs to the domain of closure of K, and then I write the equation in this form, K un, and I add and subtract this term, so this is just f plus b minus bn dun. Okay. This is not K, but K bar. So the rank condition will be proved provided the second side go to 0. Because I solve the equation 4 for f sufficiently regular, and if the second side go to 0, bn minus b dx un go to 0, this implies that the range of K bar is dense. So this is the simple idea. One way to prove that this go to 0 is to show that the integral of the square bn minus b squared d mu is 0, and the integral of dx un squared d mu is finite, is less or equal to some constant c independent of n. This is not very well written. The second condition is an a priori estimate on the derivative of un. This should be less where c is independent of n. So I will discuss some case in which it is possible to show these things. The first case is the case of the white noise, when Q is the identity, or when Q is invertible with continuous inverse. Then, to show that integral bn minus b go to 0, one use the dominant convergence theorem. So it is enough to assume that the integral over h btx squared mu dt dx is finite. Because an estimate for the derivative is very easy in this case, because one can take advantage of the inégalité de Carré du champ. That is, one consider this equation multiplied by un both sides, and then integrate, and then one take into account this property that this basic property that kun square is equal to qn kun plus q1 alpha dun square. Because since q is the identity, this will give an estimate for the derivative. So in this case, one finds uniqueness in the class of probability kernels such that it is finite. This reference is this paper with Bogachev and Reckner, JE09. A second case is when B is quasi-dissipative. Quasi-dissipative means that bx minus by x minus y is less or equal to some constant, not necessarily negative, omega x minus y. Then there is a well-known gradient estimate for the parabolic equation. This follows from dissipativity, either by the probabilistic method using the Bismuth-Elbert-Lee formula, or by deterministic method using the Bernstein method. Bernstein method means to look at the parabolic equation fulfilled by the square of the gradient of the solution. This will give comparable results with respect to the Elbert-Lee formula. Again, we obtain uniqueness in this class. This is another proof. This is also a paper in collaboration with Bogachev and Reckner. Now, let me consider the case when the noise is colored and B is general. In this case, there is not a general result of uniqueness. One has to consider in the different cases. So let me consider the two-dimensional Navier-Stokes equation with periodic boundary condition. In this case, it is possible to obtain an estimate for the un square, either by working and obtaining sharp estimate about the solution of the stochastic Navier-Stokes equation, or by generalizing a deterministic method from Bernstein. Let me say something about a possible generalization of Bernstein. So I recall that the Bernstein method allows to estimate the solution of parabolic equation when the nonlinearity is quasi-dissipative. This is an assumption which is always done when working with the Bernstein method. But in fact, one can generalize this method, showing that if there is a suitable estimate for the derivative of b n xx, then one can generalize the Bernstein method and still obtain an estimate for dx un. And in a moment I will try to explain the main idea. So what is necessary? Because obviously when if B is quasi-dissipative, if B is quasi-dissipative, that is bx minus by x minus y less or equal omega x minus y square. And if it is differentiable, this implies that b prime x h h is less or equal to omega h square. If we have a quasi-dissipativity and if b is differentiable, then you find this estimate. And now one can show that one can generalize this estimate. I will show in a moment how, in order to be able to obtain an estimate for the gradient. For instance, in the case of 2D Navier-Stokes, one can prove the following estimate, that 2 Bn prime x h h in L2 is less for any epsilon positive, there exists C epsilon positive, such that 2 Bn prime x h h in L2 is less or equal to C epsilon, a big constant, times epsilon ax L2 square times h L2 square plus epsilon norm of h square in H1. This can be done just by working on the stochastic, on Navier-Stokes equation. One consider Navier-Stokes equation, dx equal ax dt plus bx dwt, where the bx is just x gradient of x, and by using Ito formula several inequalities, one is able to obtain this. This can be obtained also by deterministic method, by working with suitable Lyapunov function. So in any case, one gets this formula. And by this formula, one finds the following gradient estimate. So in a sense, it's not as nice as the gradient estimate we obtain in the quasi-dissipative case, because here we get this estimate, d un of x just equal to e2 omega t, capital T, so some constant so here the yes. For instance, if it is strictly dissipative instead of dissipative, you find that d phi n is less or equal to some constant. So in this case, again, you get a gradient estimate, but this gradient estimate is, in a sense, very bad, because it is less or equal to an exponential of the norm h1 x squared. This is the estimate. But still, this will give uniqueness of Fokker Planck within the class of probability kernel, which fulfills this very strong assumption. The assumption is very strong, but from the point of view of Fokker Planck equation, is good enough, because what one wants is to solve a Fokker Planck equation and to show by uniqueness the Chapman-Kolmogorov equation, because then with the Chapman-Kolmogorov equation one can reconstruct the evolution. So it is important to be able to consider initial zeta given by Dirac of x. So even if this condition is very strong on the measure mu, it allows the possibility to consider delta function and then to prove Chapman-Kolmogorov equation. So this is a paper in collaboration, in collaboration with Bogachev, Rechner, and Shaposhnikov. So what about three-dimensional Navier-Stokes equation? One can try to use the same method for three-dimensional Navier-Stokes equation, but here the method does not work because this kind of estimates are too strong. It is not possible to obtain a suitable estimate of Vn prime xn HH for three-dimensional Navier-Stokes. One can get, but it is very, very bad. So, however, one can argue, as in a paper with Debuche, and in this paper is not sure because we didn't study in this paper the transport equation. But the result of the paper can be easily generalized to the case of transport equation. So we can prove that by using the same method with the paper with Debuche, that for any f regular, one has a solution of this solution which is regular. That is, it is well defined together with its derivatives. But the derivatives had a bad behavior. What you showed that the derivative grows as 1 plus ax to k. And so this derivative cannot be approached by exponential solution. And in this case, a possibility to which we are thinking about, but for the moment you have no result, is to define a different space of test function, which include this. Because you see, the result in the paper of Debuche is very similar to a rank condition, because we show that for any f regular, there is a solution which is regular. The only problem is that has a bad behavior with respect to derivatives. So this remains an open problem. I will finish about by giving some remarks about the deterministic case. So deterministic case means just q equal to 0. For instance, the result I have presented before for Navier-Stokes, for two-dimensional Navier-Stokes, also in the deterministic case. One can say that for 2D Navier-Stokes equation, we can show existence in this class of function, even for the stochastic equation deterministic. Okay. So the first important result in the deterministic case is the result when H is finite dimensional, is the result of diurnal ions. So what did the diurnal ions is the following. They take the transport equation, okay, U equal to F. This is just a transport equation. In a deterministic case, it looks simpler. So it is just dtu plus ft btx du equal to F. So the method of diurnal ions is first to construct a weak solution of this equation. This can be done quite simply. And now the idea is to regularize this solution, this weak solution. For instance, they use modifiers. And by regularizing this solution, you can write that k u epsilon is equal to f epsilon plus a remainder, which is the famous commutator, and I show that this commutator goes to 0. You see that this is similar to the rank conditions, not the rank condition, but it is natural to investigate the conditions with rank condition. I think this is... So, what in infinite dimensions? In infinite dimensions, there is a generalization of the Di-Pernal-Lyons theory in the setting of the abstract Wiener space. Today, just in and let me recall that in the finite dimensional case, what Di-Pernal-Lyons do is that by using this renormalized solution, they are able to show the uniqueness of the continuity equation, the solution of a continuity equation. As I showed before, the continuity equation is just a Fokker Planck equation for densities. So what they prove is that there is a unique solution of Fokker Planck equation which has densities with respect to Lebesgue measure. This is the result of Di-Pernal-Lyons. And now, in infinite dimensions, they, Ambrosio Figalli and Teng, Fang, and then Fang and Luo, generalize this result in the abstract Wiener setting, proving that given a Gaussian measure mu, they can show that under certain conditions there is a unique solution of Fokker Planck which is absolutely continuous with respect to mu. I think here I finish it. Thank you for your attention.
Thank you very much. Are there any questions or comments? No questions and comments yet, but there's plenty of time during the week. Thank you very much indeed.